My name's Noah Copperthwaite, and I'm very glad to have worked with the MSU Denver ESIIL Stars team this summer as an undergraduate intern. I was joined by Adam Lehman and Kevin Morales, and we were all supported in our research by Rachel Sadler, a returning ESIIL advanced intern, and our faculty mentor, Dr. Anzong Ma. We studied the evolving trends of Colorado's hydrology, and we're excited to share our results with you. I'll start our presentation today with a brief background on our research topic and an explanation of why this work is important before outlining the scope of our project. Kevin will be presenting our statewide qualitative analysis, and Adam will be presenting the quantitative findings of our case studies. Rachel will be presenting the overall conclusions of our work and the opportunities we identified for continued research. Each slide has a page number in the upper right corner. So if you have questions, please note the slides so we can answer them at the end of our presentation. If you weren't already aware, the Western United States is facing a crisis. For over 20 years now, rivers and reservoirs have been drying up as demand for water increases or even just stays the same. Annual snowpack and rainfall have remained depressed below what legislators in the 20th century planned for. A growing body of research suggests that this is the new climatic norm for the region. The water crisis is perhaps best embodied by the Colorado River Upper Basin's largest reservoir, Lake Powell. After filling to capacity and nearly overflowing in 1983, a period of drought in the early 90s put strain on the water supply, but it quickly recovered. However, since the severe drought in 2002, the Western United States has struggled to balance growing populations and economies with a declining water supply and recurring droughts. This significant decline is almost immediately visible with satellite imagery. This image series shows the decline of Lake Powell from 1985, where our study begins its analysis, to the present day, with two intermediate images highlighting the severe impact of the 2002 drought. Here in Colorado, the headwaters for much of the West water reserves, the state has undergone massive changes, both to the demands for and the availability of water. So our team asked, how have changes in climate, population, and agriculture influenced the hydrologic patterns across Colorado? With specific focus placed on the 2002 drought, each step of our analysis looked at the 20 years before and the 20 years after that date. We gathered data from the United States Geological Survey, the Department of Agriculture, and the Bureau of Reclamation, alongside Colorado Department of Public Health and Environment and the State Demography Office, to study water use, reservoir levels, stream flow, snowpack, irrigated agriculture, and population so that we could approach this topic from multiple angles. If you want more context on any of the figures we're presenting today, or would like access to their interactive features, our website displays the key figures with in-depth analyses, and our team GitHub repository has all our code and additional source data. Additionally, each slide with interactive figures has a direct link to the appropriate plot or map. And you can find a PDF download of this presentation in the chat if you want to click any of those links. I believe Kevin has also provided the two links on this page if you just want to access those. Without further ado, I'll hand things off to Kevin, who will be presenting our statewide qualitative findings.
Thank you very much for that, Noah. Regarding the qualitative analysis, what I wanted to start off with was the water withdrawals by use within Colorado. For the total withdrawals, what we noticed is that Colorado's combined surface and groundwater withdrawals have declined over 40 years. Groundwater withdrawals did spike around 1990 and 2000, likely offsetting surface shortage during the drought. For agriculture, what we noticed is that irrigated acreage has dropped by 1 million acres since the late 90s due to urban development, buy and dry transfers, and compact-driven groundwater cutbacks, where cities acquire senior water rights under a prior appropriation to support growth. As far as industrial, thermoelectric, and mining go, the post-2002 drought saw withdrawals decline. Facilities adopted conservation measures and new environmental rules that curb demand, and all sectors operated under prior appropriation and must mitigate stream impacts through augmentation plans to continuously reduce the downward stream trends that we've been noticing. As far as public supply goes, withdrawals dipped around 2000, likely due to drought conservation, then rose post 2010 with the Front Range growth. Through total use increase, per capita consumption drop thanks to efficiency in ordinances, and systems expand via rights acquisition and infrastructure upgrades. So now that we talked about human uses with water, let's observe the population and how that's affected multiple measures. So, accommodations, policies, and conservation measures that we saw affect water use on the previous slide, which have the biggest factor to consider, which is population. The mass migrations from more rural areas to metro areas are affecting the steady increase of public water supply. However, a massive decrease when it comes to irrigated culture. To further elaborate on the graph, what we've noticed is a significant increase and a continuing increase when it comes to population within Colorado, with a slight trail off in 2020 likely due to the pandemic. As far as irrigated agriculture goes, there's been a significant decrease that occurred between 1997 and 2002, likely due to the drought, but exacerbated the ongoing trend as we see a continuing decrease. More opportunities regarding the industrial and tech sections are available within urban areas, causing the influx of individuals to go to counties like Douglas and Denver. Regarding conservation measures, now that we've analyzed pure human factors, let's analyze the combination factors when it comes to both human and environmental influences when it comes to reservoir data. For a qualitative analysis regarding the reservoir storage, we analyzed 9 of Colorado's largest reservoirs in the upper Colorado River Basin that are selected for the analysis. For the 2000 to 2004 signature that we notice, the significant drop that happened, the data clearly captures the millennium drought with a sharp decline in reservoir storage beginning in 2002. This drop aligns with widespread reductions in snowpack and stream flow across the basin. For the 2004 to 2007 recovery and post 2007 decline, this is likely due to the improved runoff and temporary conservation measures initially for the 2004-2007. However, post 2007 shows increased volatility and steady downward trend reflecting persistent aridification and reduced inflows, likely from the uh, river discharge effects as well as snow water equivalency. As far as stream flow goes, what we noticed between the two time periods that are analyzing, which is 1980 to 2024 and 2002 to 2024, is that we found a mean of 931.1 cubic feet per second, whereas 2002 through 2024's mean dropped to 732 cubic feet per second, reflecting an overall 21% reduction. This shift coincides with the documented drought intensification and increased water demand when it comes to public supply areas, which is suggesting climate-driven pressures and systematic changes in watershed behavior. The harmonic structure that I developed helps emphasizes that change that occurred post 2002, as we see a complete shift in the green plot and how there's a continuing trend downward. As for snow water equivalency, between 1980 and 2024 analysis, for the 1980 to 2001 mean, we noticed 6.04 inches, while 2002 through 2024 declined to 5.33 inches, a 12% reduction. Unlike stream flow, snow water equivalency is governed almost entirely by climatic drivers such as temperature increases and altered storm tracks, along with shifts in seasonal precipitation. The sustained decline suggests diminished water accumulation and accelerated spring melt, consistent with broader warming patterns. These findings underscore the vulnerability of mountain snowpack as a climate indicator and its role in shaping downward stream hydrologic availability. For a more visual representation, we went ahead and conducted a Thiessen polygon analysis, which means that we converted the points to polygons to match a perfect rectangle, or almost as perfect as we could get. I highly encourage individuals who have had access to the link, as well as to the PDF, that they visit this interactively because we could really explore the different results when it comes to the different stations. As streamflow goes, there's been a decrease all around. Every single one of those values are going to start at -6 and end at -39 when it comes to cubic feet per second, with an overall decrease occurring at every single station. Regarding snowpack, there has been increases in certain areas, but mostly decreases everywhere else. The blue is the increased snow water equivalency, and the red is the decrease in snow water equivalency, which directly reflects the different means that we evaluated, showing an overall decrease in snow water equivalency in Colorado overall. As for the other two interactive percent change maps, we've noticed a consistent decrease when it comes to irrigated agriculture across all of Colorado, starting with negative values of -6 all the way to -94. Regarding the percent changes, and then regarding populations with counties, we notice a significant influx in more urban areas like Douglas and Denver counties, and a decrease in population when it comes to more rural areas as individuals move for more opportunities within the urban sector for tech jobs. For qualitative conclusions, the increases in populations have occurred along with associated water uses. Decreases in land use for irrigated culture have happened significantly, and decreases in snow water equivalency, stream flow value when referring to cubic feet per second, and reservoir values, which is referring to million acre through feet. In all, the conservation measures that Colorado has taken is not enough to prevent the continuing decreased hydrologic values. The trends from climate change and withdrawal factors from human activity will continue to affect lesser water values if more conservation measures and climate change mitigation are not taken. To further analyze the phenomena from this qualitative section, we decided to conduct case studies for three counties that involve a rural county, which is going to be Logan County, an urban county, which is going to be Douglas County, and a county within the mountains, which is going to be Eagle County to include snow water equivalency values. With that being said, I'll go off and hand it off to Adam to present the next section.
Awesome. Thank you, Kevin. All right, so as Kevin was saying, we did some case studies. For our case study, we chose 3 counties in very different areas of Colorado to get a more in-depth look in our data. So we chose Douglas County because it is along the Front Range, it's an intermetropolitan area, and it's rapidly urbanizing. Eagle County was decided upon because it is along the I-70 corridor, it is west of the Continental Divide, and it's located in a mountainous area. And lastly, we chose Logan County due to it being in the eastern plains of the state, more centered around rural agriculture, and it is along the South Platte River. So our hypothesis was that hydrologic changes in Colorado are linked to climate disruption. Our null hypothesis was that hydrologic changes are not significantly correlated to human factors like land use and population. So first, we did the Pearson correlation coefficient, which is a statistical calculation that provides a number between -1 and 1 that measures the strength and direction of the relationship between 2 variables. So essentially, the closer the number is to 1, the stronger the correlation. The closer it is to 0, the weaker the correlation. And then a negative number is going to represent a negative correlation where one variable increases when the other one decreases, or vice versa. So the variables that we chose for this are irrigated agriculture, population, snow water equivalency, and water discharge. So looking at the Douglas County Pearson coefficient of -0.851, a strong negative correlation between the population and irrigated agriculture is very clear. As the population grows, there's less and less irrigated agriculture as these urban areas expand. In Eagle County, we saw a very similar trend to Douglas, with a Pearson coefficient of -0.858, which is a strong negative correlation between population and irrigated agriculture acreage is evident. This is related to a growing population and there again, expansion of infrastructure. And looking at the Eagle County data again, as we predicted, a strong positive correlation between the Colorado River discharge and Vail snow water equivalency was clearly evident with a coefficient of a positive 0.824. As you can see by the side-by-side comparison of the data, when the snow water equivalency values are higher, more water is flowing in the rivers during runoff and throughout the summer. So with Logan County, we had an interesting trend. We really identified something that was outside of the others. There is a weak positive correlation between population and irrigated agriculture acreage. This is the opposite of what happened in either Douglas or Eagle County. So this demonstrates that even though the population has steadily decreased over the last 15 years, the irrigated agriculture acreage has increased over the past 8 years. So in conclusion, for the Pearson correlation coefficient data, we noticed the following. Negative correlations for population and irrigated agriculture acreage were identified, except for in Logan County where the opposite is happening. There's a direct positive correlation between the amount of snow that accumulates and the stream flow discharge for Eagle County. We also noticed there were weak correlations amongst all the other matchups. All right, so next we'll move on to our analysis of variance, or an analysis, or an ANOVA. An ANOVA test is a statistical method used to compare the means of two or more groups to determine if there's a statistically significant difference between them. So if this was done at a 95 confidence level, which means that the method used to create this range of values is good enough that if we did this kind of study 100 times, about 95 of those times the range we calculated would actually capture the true answer we're looking for. But the most important thing in these next slides, when looking at these values, just remember that the higher the S statistic value represents a greater difference from the mean of the data. You also see a p-value in these data sets. The closer this value is to 0, the more accurate the F statistic is. But all of our data resulted in a near 0 value. The variables we used for this is the population, irrigation, and stream flow discharge, as the snow weather equivalency values were not available for Douglas or Logan counties. The time periods we focused on were the pre-drought years of 1985 to 2001, post-drought years of 2002 to 2022, and the overall trends of 1985 through 2022. So looking at the population data for all three counties, an incredible outlier is apparent, with a value of 614.42 for the 2002 to 2022 time period. Significant differences in the population for each county is clear. So if looking at the graph, you'll see that Douglas County's population just continues to grow at a much higher rate, with an overall increase of actually 838% from 1985 to 2022. The growth of Eagle County has continued to grow over the years, but at a much lower rate, while Logan County has actually seen a 6.96 decrease from 2001 to 2022. Now, looking at the irrigation data, a diverging trend is noticed for the 1985 to 2022 time period, but the most significant value of 75.744 for the 2002 to 2022 time period demonstrates that this difference has increased over the last few decades. When it comes to stream flow discharge, a significant difference is evident for both pre- and post-2002, but the mean variance for the 1985 to 2022 time period is drastically different. Stream flow has changed a great deal over this time period. So in conclusion, looking at the data for post-2002 to 2022, it's clear that vast changes are happening in all three counties. The population of Douglas County has seen incredible growth in contrast to the rather slow and steady growth of Mountainous Eagle County and decreasing population for Logan County out on the plains. With an overall growing population and dwindling water availability, it's imperative that we take action to slow climate change and use water more responsibly. If the trends continue that we see here, Colorado could meet a very tough situation in the future.
For overall, we determined that Colorado's water resources are undergoing significant changes with synchronized declines in snow water equivalents, seasonal stream flow, and reservoir storage after 2002. These shifts are strongly linked to climate change, population growth, and evolving agricultural practices, leading to reduced snowpack, earlier runoff, and increased discharge variability across the state. The data and analyses we have shared with you today confirm that Colorado's hydrologic water systems are being reshaped by a combination of climatic disruption, land use transitions, and increasing water demand from urban expansion. Now, this is a complex system, so there are other factors that require further research. In any year, groundwater withdrawals supply 10 to 20% of the state's overall water use, with some counties being heavily reliant on wells for domestic and agricultural uses. During our research, we discovered that there was a lack of continuous data for this collection prior to 2000. Most test sites that we accessed through the USGS only had a few months or at most 2 years available. However, the Arkansas alluvial presents an opportunity for a case study. It had several short-lived sites in the 90s and some more recent sites that have recorded data continuously since 2005. In both our quantitative and qualitative analyses, a negative correlation between population growth and irrigated agricultural land was identified. It has also been noted repeatedly in media as rural farmers are competing with the sprawling Front Range cities for both land and water. A land use case study would be helpful to identify exactly where the population growth is occurring or specific types of urban development that is truly driving a decline in agriculture. Another approach might be to comb through all of the records of water courts to identify patterns of purchases, transfers, and leases of water rights between users. However, this would be pretty complicated as there are several interstate agreements that grant seniority to out-of-state users. Our study focused on the connection between human factors and changes in hydrologic patterns, but it's equally true that our state's wildlife is struggling to adapt to this new norm. In the high alpine zone, the growing season has significantly shortened, and the species in this habitat, several of which are now endangered, are perhaps indicators for a future crisis. In addition, we believe an NDVI analysis might be helpful in studying wildlife and their habitats, as well as agricultural changes across the state. Another factor requiring more research is the seasonal shift. In Colorado, our winters are shorter, snowpack is melting earlier and faster than historically observed. An earlier and faster snowmelt means that mid to late summer season stream flows are more reliant on rainfall, and this is ultimately leading to shorter growing seasons. And as any good study, we'd like our work to be replicated. Most of our data was obtained through federal databases, and the code for each analysis is available on our team GitHub repository, making replication accessible for anyone who would like to do so. On the next slides, we have our sources, and we'd like to thank you all for your time and attention, and thank you to ESIIL Stars for this opportunity and support during our research. We'd like to open up the floor for any questions.
Awesome job, MSU. Give the folks at Metro State a round of applause or some kind of emotion in the chat. We've got time for one question or so. If anybody would like to turn on their microphone or put a question in the chat, please go ahead. So my question was, what was the biggest challenge for you all in terms of pulling all of this together?
I'll say on my part, government websites are not friendly whatsoever. So I had to do a bunch of extra steps to extract the data when it comes to snow water equivalency values.
And I'll speak similarly that cleaning data was probably the most labor intensive step, apart from learning a lot of coding techniques, but cleaning data was the most tedious.
Yeah, learning how to use that data in a coding environment was definitely very challenging, but we figured it out.
Yeah, I think there's some stat out there that like 80% of time spent doing data science is cleaning your data and wrestling with your data. So, any other questions for MSU?
But we did all that for you. So if you want to do this for your state or do a different county case study, the code is available and the data is clean.
Shout out for open science.
Mhm.
And you're getting some comments in the chat there too, team. So great job. Okay.